Welcome everybody to our webinar on modeling species transport and surface reactions in biosensors with COMSOL. My name is Ksenia Semina, I'm a marketing manager at COMSOL UK. Our speaker today is Ross Hubble. Ross works as an application engineer at COMSOL UK. He graduated from the University of Cambridge in 2010 with a degree in chemical engineering and then went to carry out his PhD investigating carbon oxide hydrogenation reactions. Before we start, I'm going to briefly run us through some introduction to the GoToWebinar software, in case you haven't used it before. You can see control panel on the right-hand side of your screen. Please use questions pane to submit any questions as they arise during the webinar by typing them into this box. Your answers won't be displayed. Instead, towards the end of the webinar, about 35 minutes in, Ross will answer the questions that come in. Please don't miss out on this opportunity and submit your questions early. We'll try to answer all your questions, but any we don't answer will be followed up afterwards, so don't worry. Everyone will receive an email within 24 hours with a link to the recorded event, so you and your colleagues can watch this webinar on demand. Okay, enough intro information. I'm going to hand over to Ross. Please take over.
Hello and good afternoon. Welcome to this webinar on modeling species transport and surface reactions in biosensors with COMSOL. My name is Ross and I'm part of the support team at the Cambridge UK office. I specialise in the support of chemical and electrochemical applications. In today's webinar, I'm going to begin by giving you an introduction to the COMSOL Multiphysics product suite. Following this, we are going to be exploring why we might be interested in investigating biosensors within a simulation environment. I will then briefly run through the different types of physics we might be interested in investigating in a biosensor before demonstrating their application by building a biosensor model example. At the end of this webinar, there will be an opportunity for questions, and if we are unable to answer your question within the time available, we will get back to you afterwards. So what are our motivations when we simulate a biological system? Biosensors are the workhorses of biological analysis. They are often used in medical testing applications, however, may also be used academically to improve the mechanistic understanding at the molecular level of a biological system. These analysis tools are used in countless applications for the detection of biomolecules within the field of pharmaceutical, agriculture, environmental technologies, and food technology. The powerful combination of theory, simulations, and experiments has increased our understanding of the molecular level behavior of biological mechanisms, and this knowledge has yielded a myriad of methods for the detection of biomolecules in medical applications. Biosensors themselves play significant roles in drug discovery and targeting, microbial and virus detection, gene therapy, and other processes in biotechnology. Through simulation, we can investigate complex systems. It may be difficult or time-consuming when dealing with an experimental system to identify which physical processes are limiting. However, through using simulation, these influences may be quantified more rapidly. This is particularly useful when examining the design and optimization of a sensor system. Simulation streamlines design through reduction of the number of physical prototypes required and allows for potentially flawed concepts to be rejected earlier. How does COMSOL Multiphysics software fit into the simulation of biological systems? COMSOL Multiphysics offers a simulation platform for solving physical equations across a wide variety of physics. COMSOL simulation is not exclusive to chemical species transport and reaction and can simulate electromagnetics, mechanical problems, heat transfer, and fluid flow. The advantage of the multiphysics approach is that it allows for the inclusion of many different equations and types of physics to be amalgamated together into a single model with a common user interface. This approach is a real advantage for biosensor design, being able to combine heat transport, mass transport, and chemical reaction within a single package. COMSOL offers a great openness and flexibility which enables the incorporation of your own novel equations or material properties into the model. A further feature of COMSOL is the ability to turn models into apps through the application builder. The application builder enables you, as an expert user, to create a model and deploy it with your own user interface. Apps can be set up to display results, and input may be restricted to a handful of parameters within an easy-to-use interface, such that colleagues can extract the information they need without the need for simulation software experience. Today's demonstration model is available as an app for optimizing the biosensor within the application library. The workflow for building and distributing an app is straightforward. COMSOL Multiphysics lets you set up models where you can choose different ways to define your model, sweep through different parameters to compare and optimize solutions, and select different ways to present and post-process your results. Within COMSOL Multiphysics, you can use the application builder to create apps from the underlying model. This allows you to create simplified and sometimes more sophisticated applications based on your model. The form editor is flexible and allows you to include features and components from the model which you can use to restrict the inputs and outputs to only those relevant to the end user. The method editor allows you, through programming, to incorporate novel features and functionality to your application, which you cannot do in the underlying model. In order to deploy and run your apps, there are two options: COMSOL Server and COMSOL Compiler. COMSOL Server offers two useful features. It allows you to run applications either remotely or locally, and allows you to control the deployment. COMSOL Server hosts apps and makes them available due to permissions you determine with login and password support. It also allows you to control the infrastructure in running the applications on a cluster, such as which nodes or how many nodes the application solution process can use. You can use the COMSOL Server on Windows and Android, as well as web clients. The COMSOL Compiler offers an alternative to the server. The compiler creates an executable of your application together with the runtime libraries. These can be run locally, where the runtime libraries are unpacked, the application is installed, and the app is ready to run without requiring either COMSOL Multiphysics or COMSOL Server to be installed or found on the same machine. The COMSOL compiler is an add-on to COMSOL Multiphysics and requires a COMSOL Multiphysics license in order to compile apps, yet the compiled apps themselves can be copied and distributed throughout the world to as many people as you desire and as many locations as you want. COMSOL has a broad product suite, and the physics of today's biosensor model are part of the chemical reaction engineering module. This is an add-on product to the core package of COMSOL Multiphysics. The tools for modeling species transport and reactions provided within this module can be further extended with physics interfaces for heat transfer, mechanics, and fluid flow. Note also the optimization module, which may be applied to optimize designs or fit chemical kinetic data. The interfacing modules on the right here incorporate the combination of COMSOL Multiphysics with various different CAD softwares and other tools which you might work with to streamline this simulation workflow. If you have any questions about these, feel free to contact us at COMSOL after today's webinar. How does COMSOL Multiphysics fit into sensor simulation? COMSOL Multiphysics offers a simulation platform for solving physical equations across a wide range of physics. COMSOL Multiphysics simulation is not exclusive to modeling species transport and reactions and can simulate electromagnetics, mechanical problems, heat transfer, and fluid flow, as well as electrochemical reactions. The advantage of the multiphysics approach is that it allows the inclusion of many different equations and types of physics to be amalgamated together in a single model with a common user interface. The approach is a real advantage in biosensors where multiple physics are combined into one device. For instance, fluid flow physics is important element in lab-on-chip devices. Accurate electromagnetic modeling is important in simulating impedance sensing or in the modeling of biological separation processes within electric fields, for example, electrophoresis. Glucose modeling systems demonstrate a real-world example of when one might use simulation for designing a biosensor. Through combining mechanical, chemical, and electrical physics into a model, a higher fidelity representation can be developed. This in turn allows for better representation and optimization of the sensor's design for accurate measurements. Different types of physics within the COMSOL environment are set up using physics interfaces. These package up different equations which describe different physical systems or phenomena. The pre-built physics interfaces enable easy specification of physics for each application, grouping the relevant boundary and domain conditions within a single node. For example, the laminar flow interface has nodes for inlet flow conditions of velocity or pressure and mass flow, and the transport of dilute species interface has nodes to describe species flux, concentrations, and reactions, to name a few. The interfaces also contain default nodes, which are essential to each simulation. For example, the transport properties node for transport of diluted species is used to specify the diffusivities and the model species and the velocity fields they experience. These default nodes are automatically included with each physics interface to save time in the setup of models. Let's briefly discuss the different capabilities for species transport within the chemical reaction engineering module. The list here represents the physics interfaces available with the chemical reaction engineering module and some of the relevant functionality from the CFD module. The interfaces are separated into distinct themes: fluid flow, heat transport, and chemical species transport. At the top here we have mass transport and reactions. We have transport of concentrated species and transport of diluted species. These are used to determine the diffusive movement of species and may be coupled with fluid flow interfaces to incorporate convection. Migration can be added to include the influence of electric field on the transport of ions. We also have momentum transport, which is usually referred to as fluid flow and represented using CFD. In COMSOL's chemical reaction engineering interfaces, we have laminar flow, reacting flow, and porous media flow interfaces already included, which is important for modeling porous domains like you might find in a chemical reactor or in a fuel cell. With the addition of the CFD module, you also obtain the capabilities to model turbulent flow and multiphase flows. Heat transport is a key element in many chemical processes, with reaction rates often being sensitive to temperature, and reactions may also generate heat or require cooling to operate at the required reaction rate. Hence, the capability to model thermal transport within your system is important. The chemical reaction engineering module contains the physics interfaces necessary to describe convective and conductive heat transfer in both free and porous media. Finally, the reaction engineering interface provides a means to define reactions and compute the behavior for ideal reaction models, such as perfectly mixed batch reactors or plug flow reactors. This allows you to examine the kinetic behavior of your system under ideal conditions. The reaction engineering interface is a 0D physics interface used to compute the mass balances and energy balance equations describing ideal reactor systems. It assumes a perfectly well-mixed and well-defined reactor, and while this is not the case for our biosensor, it can be used to quickly generate the required physics interfaces in a space-dependent model. Once you've defined your reactions in the reaction engineering interface, a 1D, 2D, or 3D space-dependent model can be generated from it, with the related reaction and transport nodes pre-populated with the necessary reaction data. This simplifies the model setup and for complicated reaction systems and leaves only a few boundary conditions and properties to be specified, for example, inlet velocity. The transport interfaces take a homogeneous approach to modeling the transport of species, and these use correction factors such as the Bruggemann correlation to account for the influence of porosity on the effective diffusion coefficient. Within COMSOL, reaction kinetics can be described automatically using the predefined mass action law or through the input of your own analytic expressions based on concentration. The CRE module can also be coupled with the fluid flow interfaces and the heat transfer interfaces to couple these to your chemical reactions. In terms of when to use each transport interface, the transport of diluted species interface is appropriate when the solute only interacts with other solvent molecules. This model uses Fick's law to describe the flux of species and is in general applicable only to dilute species, that is, modeling species with a low mole fraction relative to the solvent. For multi-component systems where each species has significant interaction with one another, it is more appropriate to use a multi-component transport model. COMSOL offers both Maxwell-Stefan and mixture average transport models to describe species flux in this case. So with this is when there are interactions between different solutes and the solvent as well. Knudsen and Dusty gas models are also included. Surface reactions are important in biosensors as well as more general heterogeneous reactions such as reactions on catalytic surfaces. Instead of bulk consumption rate across the domain, the rate of reaction is described as a boundary flux, acting as a source or sink of material. At the surface, concentration gradients will develop to match the flux With the demand from the reaction, in mass transfer limited systems, significant concentration gradients may occur, and the transport of species will become limiting, reducing the observed reaction rate. It may also be relevant to include some electrochemical physics interfaces when modeling bioelectrochemical sensors. Primary and secondary current distributions are modeled in COMSOL and take an ohmic description of electrolyte resistance. The primary current distribution relates the electrode and electrolyte potentials by the equilibrium electrode potential, whilst the secondary current distribution interface includes the influence of electrochemical kinetics. The tertiary current distribution explicitly considers the movement of ions in the electrolyte using the Nernst-Planck equation to describe both transport of both charged and neutral species. This is the most complex and the most rigorous of the interfaces. Electroanalysis provides a convenient interface for modeling mass transport and electrokinetics where there are no significant potential gradients. This is used in one of the examples in the application library to model a glucose sensor. These interfaces may be used for the simulation of biosensors or in examining electrodialysis and other biochemistry simulations. So we're now going to move on to looking at how we might design a biosensor. The schematic here shows one possible arrangement of a biosensor. Here we have enzyme immobilized on the detected micropillars with a flow from the left to the right. The enzyme is attached to gold-colored concave parts of the pillars and can only attach to a specific group of biomolecules. This high specificity of enzymes represents one of the main advantages of biosensors. So how does a biosensor work? In this biosensor, the biomolecules are absorbed to the enzyme-coated pillars, where they can be measured by a spectroscopic technique, for example, fluorescent detection. Enzymes serve as excellent receptors since they can only attach to a single biomolecule or a very specific group of molecules. A second reaction quenches the absorbed biomolecule, decreasing the fluorescence, weakening the signal from the detector, and since quenched molecules no longer emit light. The pool geometry has symmetry planes which can be used to reduce the simulated system size. Reducing the size of the system and using symmetry boundary conditions will lower the number of mesh elements required, and thus lower the computational requirements. This can yield faster simulations without any loss of fidelity. The full geometry can be restored from the reduced geometry and post-processing using mirror data sets. The model uses three main physics interfaces to describe their reactions: flow and diffusion within the system. The laminar flow interface describes the fluid flow within the channel, solving the Navier-Stokes equations. The fluid properties are assumed to be those of water, with a flow of 0.2 millimeters per second entering the left-hand side of the sensor, with the flow exiting at the outlet, assuming a zero pressure boundary condition. Since the concentration of the biomolecule within the fluid can be assumed to be dilute, we can use Fick's law to describe the diffusive and convective transport. The inlet concentration is set to using a time-dependent Gaussian pulse, with unreacted species leaving via the outlet. At the surface of the pillars, we have the two reactions going on: the absorption and desorption of the biomolecule P onto the pillars, and then the quenching reaction of the adsorbed species PS. Here we have the expressions in the middle representing the balance on the surface concentration of P and Q. Okay, so now we've had an introduction to building a biosensor. Let's move into COMSOL and make the model. Opening COMSOL, we're presented with the new screen to start with. The two options are either blank model or model wizard. It's always recommended to start with the model wizard since it pre-populates the model builder tree for you with the required physics interfaces. The model wizard asks a series of questions about the model to ensure we get off to the right start with the interfaces, study types, and couplings. Here we're going to select 3D space dimension to represent our biosensor. We recommend using the lowest space dimension possible for your application, as this reduces the memory requirements and leads to a faster simulation. For many chemical reaction problems, a reactor system is tubular and may benefit from the use of a 2D axisymmetric component. The physics selection screen presents you with an array of physics interfaces grouped by the types of physics to which they are applied. Information on what each physics interface is capable of is given in the right-hand side of the screen here. So we can add the transport of diluted species interface now by double-clicking here. And we can also add in our laminar flow by selecting it from single phase here. And finally, we can add in our surface reactions. For the surface species, we can name them CSP and CSQ. And for the bulk species, we can name it C_B. So moving on to the study node, this screen gives the list of study options. The list is not exhaustive of all the possible studies and is selected based on the physics interfaces used. I'm going to use the time-dependent study for this example, and we'll just click Done. We're now presented with the COMSOL desktop. The main windows to look out for are the model builder tree here, which gives a hierarchical overview of our model structure. The settings pane here, where we enter in the values and parameters, and the graphics window here, where the geometry is displayed and where selections, boundaries, and domains can be made. Working from the top of the model builder tree, we're going to start with the parameters, and to save a little time, I'm going to load in a list of parameters from file. These include values for the initial concentration, different kinetic parameters, and geometric parameters, as well as information about the flow velocity. Moving down to the definitions node, I'm going to import some variables from a text file. So to create a variables node, we just right-click definitions and select variables. And again, load them in from the file. So here we have variables for the reaction rates of absorption, desorption, and quenching, and an expression for the inlet concentration. The term GP1 here represents the Gaussian pulse function, which we're going to use to define the time-varying nature of the inlet concentration. To add a function, we right-click, select functions, and go Gaussian pulse. And I want to set this at 20 seconds in with a standard deviation of 2. So we can just plot that to see what it looks like. Once the variables have been fully defined, we can move on down to the geometry. I'm going to insert the geometric sequence. Just to save a little bit of time here. And then we click Build. We should be able to see our biosensor. You can see that it's already had the symmetry taken of it. So this would have a symmetry plane here and a symmetry plane here. So now we've selected our materials, we can add in then we've created our geometry, we can add in materials. So I'm going to select a material from the library. And we're going to say it is water. So we'll use built-in and select water. Double click. And just hide that away. So when we create a material, it automatically selects all of the domains, so it's already defined as water. Once we've set up the materials and geometry, we can move on to defining the physics. The laminar flow interface has default nodes for fluid properties and wall, and we just need to add in nodes to represent the inlet and the outlet. So to add an inlet condition, I'll right click here and select inlet. We can specify our inlet flow based on velocity, pressure, or mass flow. And I'm going to take it as U in, which was one of our parameters we defined earlier. We can now apply an outlet condition to represent the outlet of the sensor, which we'll apply here just by selecting in the graphics window. This specifies, we have to also add in a condition for our symmetry nodes. So I created selections in the geometry earlier. So these are just predefined namings for different boundaries. So this one represents the symmetry boundaries here. So now we've defined the flow, we can move on to the transport of species. We can specify the diffusivity of P by typing in D here, which was our parameter for the diffusivity. We can then couple this to our laminar flow just by using the drop-down box here and selecting velocity field. If you wanted, you could also create a multiphysics coupling and use flow coupling there. So if we did that, it will automatically show you the flow coupling here. In order to quantify the flux of species from the bulk to the surface, we can add a flux node. And we're going to do this by selecting this. And this is represented by minus R adds, so the adsorption rate, plus des, so the desorption rate. And we want to apply this to the reacting surface boundaries. So you can see that that's being applied to the gold sections of the pillars there. So we don't actually have any species coming in or out at the moment, so we need to add in our inlet condition, our inflow condition, sorry. And we're going to say this is represented by our C0 variable, which we defined up here, which is our base concentration multiplied by our Gaussian pulse. And then as we have an inflow, we also require an outflow condition. So we'll apply that to the outlet. So now we've specified how our species behaves in the bulk, and we've specified our flow. We just need to specify our surface reactions now. So if we move along and select reacting surface, because we're only computing the surface reactions on the reacting surfaces, we can add a reaction node to represent the surface couplings. So surface reactions not only allows you to couple regular reactions with the surface, you can also couple with electrode surfaces as well. So if you had a current distribution interface, you could relate the current to the reaction there. So for this, we have the reaction represented as R adds minus R des, and then we also have the quenching term as well, minus R quench. And then for species Q, we have R quench. So we just need to apply that again to the reacting surface. So now we've defined our physics, we can mesh and compute the study. Since the study takes a few minutes to compute, I'll move over to a solved model to examine the results. The solved model here uses two study steps. The first solves for the fluid flow, and the second solves for the transport of dilute species and the surface reactions. In this case, the fluid properties are unaffected by the concentration of P, so the flow can be solved as a stationary problem. The second time-dependent step then automatically takes these values for the flow field and uses them to couple to the transport problem. This approach to coupling flow and species transport reduces the overall computational time, since the flow solution does not need to be computed at each time step. So if we look at the results, we can see how the velocity field behaves. So we have the speeding up and the narrowing of the channels. We have the pressure field, and we also have our concentration surface here with it varying in time. So if we set it at a different time, say 50, we can see the progression of the concentration through the sensor to the outlet. Again, we can also look at the concentration of the adsorbed species on the surface. So in this case, this is looking at the surface concentration of species P. And using the average operators, which are defined up here, this is just one of the component couplings. So it takes an average of the concentration on the surface here. We can look at the varying concentrations of P at different points in the biosensor. So this was a quick demo of the biosensor example, and I hope you've enjoyed it. If you want to investigate the model further, it can be found in the chemical reaction engineering branch of the application library. So now I'm going to hand over back to Ksenia.
Thank you, Ross, for your presentations. We are going to answer your questions now, so we open for your questions. And we already have quite a few questions, so I will better start now. So Ross, first question, can you build this model with the reaction engineering interface?
So if you want to use the reaction engineering interface, we can just open it quickly. So if we go new model wizard, we'll take 0D and then go reaction engineering and add it. We can then click study and select time dependent. So with this one, we can just quite easily type in a reaction. So if we go P goes to P adds to represent a surface species, we can then click apply, and then we can add in a second reaction to represent our quenching for our quench reaction. So P surface goes to Q surface, and then we can use that to generate a space-dependent model. So if we click that, we can then select how we want to define our physics interfaces in our 3D model. So if we want to have a laminar flow, we can also add in heat transfer. And if we just click create, it should create a new component which has all of the physics interfaces, as well as a chemistry interface, which just collects the reactions and then feeds them into the nodes here automatically. We also have the surface reaction node predefined as well.
Yep, thank you, Ross. Straight to the next question. Can we modify the transport equations for the component?
So if you go to the transport properties, you can modify your diffusion coefficient. And if we want to look at a porous domain as well, you can just add the check that box and then add a porous media transport property in. And then you can set how you want the tortuosity to be modeled as well manually.
Yep, thank you, Ross. Straight to the next one. Where to look at those coupled equations if we want to?
So if you want to look at the coupling, well, many of the equations are just shown in the equation section here. So that's how you can see where the variables are being used. And then normally when you have a coupling, it just blanks out which variable is being supplied by the multiphysics coupling. So here we have FC1 representing it passing the variable U to the transport related species interface.
Great, thank you. Next question. Audience, thank you so much for your questions. How do you extract the full data set from a model after using symmetry planes?
So if we go back to the original biosensor model, we have the data sets here, and it's using a mirror 3D data set. So if we just plot this one, we can see how it's behaving. So this one is representing the full data set, which is taken. You can specify a plane where the symmetry plane is, and then it will apply a mirror plane there and replicate the data. So to do that, you just want to go more 3D data sets and then mirror 3D. And then that just allows you to specify where the symmetry plane is.
Okay, great. Hopefully it answers the audience questions. If I have a CAD drawing, how can I reduce it to use symmetry?
So if you have a CAD drawing, you'll import it in the geometry node here. And currently the geometry here is created using the COMSOL primitives. And if this one does symmetry by adding in an additional block and then doing a difference to cut away along the symmetry plane. So you can use a block and a difference to remove parts of the geometry, or alternatively, you can use a work plane to partition your domain, and then you can use the delete entities if your symmetry plane isn't easily lying on a Cartesian coordinate basis.
Okay, straight to next one. How easy is to add turbulent flow to a model?
Well, it's quite easy to change the laminar flow to turbulent flow. So if we just select the laminar flow interface and then scroll down, we can select our turbulence model type. So COMSOL has the Reynolds average Navier-Stokes approach and the large eddy simulation. If we just select RANS there, it will select change laminar flow into turbulent flow, and then you can select your turbulence model as well. So COMSOL has quite a few turbulence models depending on which one you want.
Great. Straight to the next question. We've got a lot of questions for you, Ross, today. Can we modify the structure of the transport equations? For example, if we want to apply a different diffusion equation, not using the fixed law.
So if you want to use a different diffusion equation, then I'd probably use the concentrated species equation. So you can create that by using the selecting the physics interface here and using the concentrated species. So then this one allows you to use mixture average, Maxwell-Stefan, or fixed law. And if you had your own equation, which wasn't one of the pre-built interfaces, you could use one of the mathematics interfaces to specify it as well.
Great, thank you, Ross. Hopefully it answers question. We have time for a few more, I think. So what is the best way to examine different designs of biosensor?
So if you want to examine different designs, one way to do it would be to add in a parametric sweep study. So with this one, you can create a parametric sweep and select the different parameters you want to change and optimize. So for instance, this one, you can select the different radiuses and dimensions of the biosensor. And if we have a quick look at what the app does for this, it's quite interesting. So if we just click run application, it's coming. So with the app, you can limit the sort of inputs and which parameters are used and present it in a sort of an easier to look at way. So here you can select the input velocity and the different things, and this would help you optimize your design so you can change the geometry and then update. And then you can look at how the different outputs change with your different settings.
Okay, great. I think that now brings us to the end of the Q&A. And as I said before, any unanswered questions will be followed up after today. And sorry, we didn't have a chance to answer all of your questions, but don't worry, we will come back to it today. So now I do want to bring your attention to a lot of additional resources which might help you to learn more about COMSOL Multiphysics. So we do have a lot of further resources that you can refer to after today's webinar. So if you want to learn more about COMSOL Multiphysics and in particular about our application builder, you can access additional resources on our website comsol.com. Also, we have launched the COMSOL Learning Center. This is particularly of interest to our existing users. You can find many videos to help you learning how to use the COMSOL Multiphysics software. Also, I would like to bring your attention to COMSOL conference. The European conference will happen in Cambridge, UK this year on 24th to 26th September. The registration is open. Please check out our conference page. It's a great opportunity to meet other COMSOL users, listen to keynote presentations from very well-known organizations, as well as participate in panel discussions on various topics. Please do check out panel discussions. So if you have any more questions about today's webinar or about your simulation needs in particular, please do get in touch with COMSOL. You can see a contact us link on the slide. Also, if you go to our homepage, you can request a demo of the software if you're interested to learn more about COMSOL and try it for your specific simulation needs. And please fill in the very short survey to give us your feedback that will appear immediately after the webinar is finished. Thanks again for attending our webinar and all your great questions, and thanks again to our speaker Ross today. Everyone, have a great afternoon. Bye.